Welcome to Lecture 1.2, Inclusion-exclusion. Throughout this course, we will be counting things. The mathematical field of counting is called Combinatorics. One of the most basic things to count is the number of elements in a set. For example, consider the following very easy problem. There are 60 cats and 40 dogs at the local shelter. How many animals are there? Well, there's obviously 100 because every animal is either a cat or a dog, so you just add them up. Things become harder when the sets are non-disjoint. For example, consider the following word problem. An apartment complex houses 50 families. 15 of them own dogs, 20 own cats, and 25 own neither. How many people own both cats and dogs? So this is something that, even if you've never learned how to do this, we can probably figure out just because there's not too many possibilities. So if this is the universe, that is the apartment complex, let's draw a Venn diagram. So this represents dogs. This represents cats. And now let's see, we have 50 total people, 25 of them own neither, so they're out there. And now what else do we know? We know that the number of people that own dogs is 15, and the number of people that own cats is 20. So if we just add those up, 15 plus 20, we get 35, and 35 plus 25 is 60. So that tells us that we've double counted. So we've overcounted by 10. So there are 10 people that own both. I claim that at least seems reasonable. Let's check to make sure that it pans out. So if 10 people own dogs, then there are, well, if 10 people own both, then there have to be 5 people who only own dogs and not cats because there's 15 that own dogs. And if 20 own cats, then there has to be 10 that own cats and not dogs. So now if you add this up, again, these little regions are all disjoint. 25 own neither, 5 own only dogs, 10 own both, and 10 own only cats. You add those up, you get 50. So that's something that you probably could have done if I had just given you this problem and asked you to pause it. But what you do without realizing it here is inclusion-exclusion, where you subtracted off this intersection because we're double counting. So that's the main topic of this lecture. Okay, so that's what we'll be doing. Later in this course, we will encounter other counting problems, ones that have nothing to do with these non-disjoint, these overlapping sets. Problems that involve permutations, for example, such as how many ways are there to choose 4 teams out of 25 to play in the college football playoffs? Here's a related question. How many different ways are there to rank the top 4 teams out of 25? So notice that I'm asking different things. In the first one, I'm asking how many ways are there to just select the 4 teams in any order, to pick a size 4 subset. And in the second one, I'm saying specifically how many ways are there to rank team 1, team 2, team 3, and team 4. So there's obviously going to be more of those because for every possible 4 teams that we pick, there are 4 factorial ways to rank them. Okay, so that's all coming up in later lectures. This lecture is going to be focused on this problem, what we just did, called inclusion-exclusion, without even realizing it. Let's start with a definition. A partition of a set A is a set of one or more non-empty subsets of A. Let's call them A1, A2, A3, etc. There could be finitely many, or there could be infinitely many. But we require that every element in A is in exactly one set. Symbolically, we can express this with the following 2 conditions. First of all, A is the union of the individual subsets, the AIs. And secondly, for distinct I and j, the subsets AI and AJ must be disjoint. So these subsets, the AIs, are often called blocks of the partition. We can think of partitions of everyday objects. For example, suppose A is the set of all pets. Then let A1 be the subset of all dogs. I can't spell, there we go, dogs. Maybe A2 is the set of all cats. And A3 is the subset of all fish. And we can keep going. We're going to have many of these. And let's check the conditions. So the set of all pets is the union of individually of the set of all dogs and the set of all cats and the set of all fish and so forth. That holds, assuming we complete our list. And secondly, this second condition just says that these blocks are disjoint. So there is no such thing as a pet that is both a dog and a fish, or a cat and a fish. So it's just a way to group your set into logical families. You can also talk about, say, the set of all people. Maybe P is the set of all people. And let's let P of, let's pick a year, 1984, maybe is the set of all people born in 1984. And, maybe I'm a little ambiguous. Maybe I can say all people, let's say, who have ever lived. So P 1983 is similar. And let's just define Pn to be the set of all people born in the year n. And here I'm allowing n to be positive or negative. And so clearly P is the union of all of the P's. I'm going to say of all the Pn's from, well, I'm recording this in 2019. And n equals, I'm not really sure where we're going to start because it's not clear when the first human was born. But if we did know, then this would be a partition as well. Because again, every person, it belongs to one of these subsets. Every person who has ever lived, assuming that we are, assuming that the current year is 2019. And also, distinct sets clearly have to be disjoint. Okay, so those are two everyday examples. Let's move on to some more abstract mathematical examples. Consider the following set A, consisting of 4 elements, lowercase a, b, c, and d. Here are some examples of partitions. So the first one has 3 blocks, a set containing A, set containing B, and the subset containing C and D. The next one has 2 blocks, first containing A and B, and the next one containing C and D. And then the last one has 4 blocks, each of the 4 individual size 1 subsets. So now sometimes for ease of notations, it's just easier, there's a lot of braces in here. We don't need to write those. So sometimes we'll write things like A, B, C, D, or I think what's probably more common is to write A slash B slash C, D, something like that. So this here is going to be A, B slash C, D, or A slash B slash C slash D. The commas work too. You just don't need to write all these unnecessary braces. Here's a quick and easy proposition. If A is a finite set, and we have a partition of A into n blocks, notice that this has to be finite because by definition the blocks are non-empty subsets, then the size of the set A is equal to the sum of the sizes of the individual blocks. And that makes sense. If you think about it, the total number of people who have ever lived, you can just add them up year by year. Add up the number of people who have lived who were born in 1984, plus the number of people who were born in 1983, and so forth. The total number of pets is, you can add up the number of cats, plus the number of dogs, plus the number of fish, and so forth. Okay, and let me finish with one quick notational comment. So I've already told you how partitions appear. The shorthand notation A, B, C, D, and this we can write as like AB/CD, and it's understood that these are the actual blocks. And that's what motivates this notation is by calling these things blocks. Well, similarly, if we just know that the partition is abstractly n blocks that we called A1 up to n, we can write the partition as A1/A2/ ... up to AN. By the result that we just saw, if we have a counting problem and we recognize that it actually is a partition, then it becomes much easier. For example, consider the following word problem that is very similar to the one that we saw a couple slides ago. All freshmen in the Honors College must take one of 3 classes that are offered at the same time: math, computer science, and econ. The enrollments for these classes is 30, 50, and 20 respectively. How many honors freshmen are there? So this is a partition. So we have our set of, you probably don't need to write this down, but just to be pedantic, I will, all students. Let's say that AM is all students taking math. And I should say, when I say all students, I mean all of the Honors College students. That's our universe. Let's say AC is all students taking CS. And then AE as all students taking econ. So this is a partition. We can write that A is AM union AC union AE. We sometimes again write the partition AM. So it's not really that helpful to actually use, it's not that helpful to use this notation with the slashes. Also, sometimes they're vertical, completely vertical. They don't have to be angled. So it's not really that useful to use this notation if we have something like this, because the union is just as easy to write as a slash. It's more helpful when we actually have things like our set consists of A, B, C, D, E, and we want to talk about strings like A, B, E as a shortcut for the subset A, B, and E. Okay, so going back here, this is a partition. These things are disjoint. So obviously, the size of A equals the size of AM plus the size of AC equals the size of AE. Oops, that should be a plus. And this is 30 plus 50 plus 20 equals 100. If you were to draw a Venn diagram of this, they would actually be disjoint. AM, AC, and AE. So it makes sense, 30, 50, and 20. That you don't have any overlap, so you're not going to have any overcounting like we did before. Okay, so that is the easy case, is when our counting problem, when the things we are looking at is actually a partition. Here's an example where we do not have a partition. So the subsets are not disjoint. And I've made this a little bit easier by making there be only 2 subsets instead of 3. But in the next example after this, I will go back up to 3 again. Okay, so this is a lot like the example that we saw in the beginning. So the Honors College has 100 students, all who major in either math or CS. Now we don't have to worry about the universe because every student majors in one of these 2, so there's going to be nobody outside of here. So if there are 45 math majors and 60 CS majors, how many double majors are there? Well, we'll do what we did before, just add them up. We get 105, so we have double counted by 5, so we put the 5 there. And now we have 45 math majors. That means that 40 must be only math majors, and of the 60 CS majors, there must be 55 that are only CS majors. So notice what we did here is, let's, how do I want to say this? The total number of students is the union of, I'll call these sets M and C. So the union of M and C, we just added up the number of math majors, then we added up the number of computer science majors, and then we had to subtract off the number of double majors, those that majored in math and computer science. This is this inclusion-exclusion in the special case of having two sets. Here it is written up formally. The law, or the principle of inclusion-exclusion for two sets, says that given two finite sets, A1 and A2, the size of their union is equal to the sum of the individual sizes minus the size of the intersection. Here's a harder example because there are 3 subsets and it is not a partition. So let's consider the same honors college with 100 students and all of whom major in math, CS, or econ. So we're adding a major this time, econ. If there are 45 math majors, 50 CS majors, and 32 econ majors, then how many double and triple majors are there? Now this is a little bit harder because it's not clear what to do right away. You can, let's see, let's add up 45 plus 50 plus 32, and what is that? That's 95 plus 97, 127. So we're double counting by somehow by 27, but then there's double major, there's math CS double majors, there's CS econ double majors, and there's math econ double majors, and then there might even be triple majors, and it's not clear how those get put together. So here I think it's better to just show you the answer, and once you see the answer, from there we can deduce what the laws are. Okay, so here is the answer. So we can check that this works. So the number of math majors is 25 plus 12 is 37, 39, and plus 6 is 45, and that checks out. The number of CS majors is 31 plus 12, that's 43, 44, 45, 50. And then the number of econ majors is 19 plus 6 is 25, plus 5 is 30, plus 2 is 32. And let's verify that, well, let's just check. If we add these up, the number of math majors plus the number of CS majors plus the number of econ majors equals, we get 127. So we've somehow accounted for, overcounted here because we only have 100 students in total. Okay, so here's how I'm going to describe, here's how I like to think about this, what's going on. So let's put those 100 people in the auditorium and let's take attendance and let's say everybody who's a math major raise your hand. So we get 45 people and we have a tally sheet. So we make 45 tally marks, these down here, and so we do this and we get 45 tally marks, and then we say, okay, everyone who's a computer science major raised their hand, and we get 50 of those, and then we get everyone who's an econ major raised their hand, and we get 32 of those, and overall, and now we have in our tally marks down here we have 127 of them. So we have to say, okay, who did we double count? Let's remove the tally marks for the people who we double counted. So who did we double count? Well, we actually just double counted, let's see, so we double counted these 3 people, the people who were double majors in math and CS, and we double counted the math and econ double majors, and we double counted the math, econ, and CS double majors, and we actually triple counted the triple majors. However, this little piece, these 12 students here, it's not easy to represent this with unions and intersections. So rather, instead, what we have is we have these intersections that are these sort of flower petal shaped. So let's subtract off those. So let's subtract off everyone who majors in math and CS. Subtract off everyone who majors in math and econ. And let's subtract off everyone who majors in math and, in CS and econ. So now, the 12 math CS double majors, the 6 math econ, and the 5 math CS, everyone there, we have accounted for them. We have removed tallies because we double counted them. However, we're not quite done yet because there's one problem, the triple majors. These two people, let's see how many times we've counted them. So we've counted them 3 times. We've written down tallies 3 times when we did roll call for each of these. However, we have removed 3 tallies for each of them as well because we removed a tally when we counted the double majors, all 3 of them. So at the end of the day, for each of these 2 double majors, we have added 3 tallies and removed 3 tallies, so we haven't actually counted them. So we have to add them back. So we have to add back M intersect C intersect E. Okay. And now we can check. Let's check that this works. So 100 is, let's see, 45 plus 50 plus 32. That's 127. Let's subtract off M intersect C. That's actually 14. So that's minus. Oops, I have the wrong pen. Let me try that again. Minus 14. Subtracting off M intersect E, that's not 6, that's 8. So minus 8. Oh, let me try to stick with red. See if it's minus 8. There we go. And then minus C intersect E, that's 7 right there. Notice how we are, all the triple majors, we have subtracted off these 2 3 times, and we've added them 3 times. And finally, we have to add back those triple majors, so that is 2. And you can check that this is 127. We've subtracted off. This gets us down to 113. This gets us down to 105. This goes down to 98. We add 2, and we get 100. So yes, this checks out. Here is the law of inclusion-exclusion for 3 sets, written formally. So given finite sets A1, A2, and A3, the size of their union, you can just add up the sizes individually. Then you have to subtract off the sizes of each pairwise intersection, and you have to add back the size of the intersection of all 3. So hopefully now you're seeing why this is called inclusion-exclusion, because you have to include things and you have to exclude other things and then include something else and so forth. So not surprisingly, this extends exactly how you would think it would, to not just 2 sets or 3 sets, but to 4 sets, 5 sets, etc. It's surprisingly hard to write as a formula because, let's think about how you would try to write this. So suppose you had, let's see, where do I want to do this? Suppose you have n sets, then A1 union AN, you can start off pretty easily, is, actually, let me before I do that, let me do the case of 4 sets. So I'll just do that here. So A1 union A2 union A3 union A4. You just add up the sizes of the individual sets, A2 plus A3 plus A4. I'll do this quickly. And then you have to subtract all of the pairwise intersections. So A1 intersect A2 minus A1 intersect A3. But there's a lot of these, so minus A1 intersect A4 minus A1 intersect A5. Sorry, there's no 5. I'm just A2 intersect A3 minus A2 intersect A4. I was on autopilot there. Minus A3 intersect A4. So there's 6 of those. We'll learn how to count how many of those there are in soon lectures, in upcoming lectures. And then we have to add back the set of all triples, A1 intersect A2 intersect A3 plus A1 intersect A2 intersect A4. What else is there? Plus A1 intersect A3 intersect A4. And then we have to add A2 intersect A3 intersect A4. So we got all 4 of those. And then we have to subtract off the intersection of all 4 of these. A1 intersect A2 intersect A3 intersect A4. So I think you get the pattern. You're basically adding up all the singletons. You're subtracting off all the doubles. Adding the triples, subtracting the quadruples, and so forth. So you can imagine how I didn't actually give you the formula for n sets because I think you see the pattern. And how would you actually write this nicely? I mean, I'll try. Let's see. So how do you add these things up? So it's a set of all AIs minus the set of all AI intersect and the sizes of the intersections, pairwise intersections, plus, I guess we can do this, the set of all AI intersect AJ intersect AK. So maybe I should write I equals 1 to n. I should write I is different than j, and I can write I, j, k distinct. And then dot, 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 plus, minus. It's going to depend on whether n is even or n is odd. A1 intersect A2 intersect AN. And you could, and if you want to, you could probably say, if you wanted to be precise about this, you could replace this plus or minus. You could make this a plus, and then in here you could put a -1 to the, is it n or n plus 1? So -1 to the n. Let's see, when n equals 4, this is even. This last one there's a negative sign here, so when it's even, this is negative, and when it's odd, it's positive. So let's say n plus 1. If you really wanted to do it, you could write it like this. But I don't think you really get much by this. This is an exercise in notation, and if you really wanted to make it nice and formal, it would be even messier than this. So I think it's fine if you see the case with 2 sets and the case with 3 sets to just say that the pattern generalizes in the obvious manner. I want to conclude this lecture with a short discussion of why it is straightforward to modify inclusion-exclusion to the theory of probability. I don't want to spend too much time on this because probability is not the focus of this class, and we have our own upper division math course on probability, as do most universities. Okay, so let's get started. Here I have modified the principle of inclusion-exclusion using slightly different language. I'm not going to define everything formally, as I think it should be clear from the context as to what it means. And I'll describe it a little bit more as we go through it. So suppose A1 and A2 and A3 are no longer subsets of A, but suppose these are events. So think of having 3 football teams, Team 1, Team 2, and Team 3, and A1 is the event or the scenario that Team 1 wins. A2 is the scenario that Team 2 wins, and A3 is the scenario that Team 3 wins. And suppose they're not playing each other. They're just playing on a random day in a random team. So then the probability that A1 or the probability of A1 and A2 and A3 all happening is the sum of the individual probabilities that they happen minus the probability that A1 and A2 happen, that A1 and A3 happen, and that A2 and A3 happen. We'll say the probability of A2 and A3. So we have to subtract those. Then we have to add back the probability that all 3 happen. That all 3 happen. So here, notice I've been saying, well, when I say A union B, or I guess I've been saying the second one most. When I've been saying A and A intersect B, I've been meaning A and B. So the probability that A1 and A2 happen. And then I didn't say it here, but I should probably say the probability that of A1 union A2 union A3 is really the probability that at least one of these things happen. So that means that A1 or A2 or A3 happen or win a game. Here's a picture to go along with this. So here, think of probabilities as areas of regions. And the total area of the universe, which is represented by this box, must be equal to 1. So think of that like if you add up all possible disjoint events, like flipping a coin, the probability of a heads plus probability of tails is 1. If you roll a 6-sided fair die, the probability of getting a 1 plus the probability of getting a 2 and so forth adds up to 1. Same thing here. So every possible event is somewhere here in this universe. This, of course, there's a lot of symmetry. This is not very well reflective of the hypothetical scenario I said when you have football teams that win at vastly different frequencies. So if let me just draw a hypothetical scenario there. So if this is the universe, maybe the event that maybe A wins like 80% of the time, that might look like this. Maybe B wins, I don't know, about 50% of the time. That might look like this. And maybe C only wins when A wins for some other weird reason. That could happen. So you have something like this. So if that happens, then C's out. So C doesn't necessarily have to play. Well, obviously C and A can't play each other, but I don't know. Maybe there's some reason why there's one really, or maybe there's a couple really bad teams, and that they only play anytime C plays a bad team, A plays a bad team, so that they both win. I don't know, something like that. But this is a scenario where the outcomes of the games of A and C are not independent of each other. They are highly dependent on each other. So that's a concept in probability. Again, I'm not going to focus on it, but I'll tell you, A and B are independent. Here's a good way to think of it. Flipping a coin and rolling a die back to back. They don't affect each other. So the probability of getting a heads and then a 2, how do you do that? Let's just write this up. The probability of getting a heads and then getting a 2 when you roll the die is just, how do you do that? You take the probability that you get a heads, which is 1/2, and you multiply by the probability that you get a 2, which is 1/6, and you get 1/12. And that's actually the definition of what it means to be independent, that the probability that both events happen is the product of the individual probabilities. And finally, Bayes' theorem for conditional probability says the following. So this notation means the probability that A happens given that B happens, or A conditional on B. Now let's think about what that means just intuitively. So with this picture, so what's the probability? So let's suppose we already know that B happens, that we are in this circle here. Nothing else matters. So we already know that happens. Then what is the probability that B happens? Well, in this case, the answer is well, here's the event that that A happens, not B. So if we know that B already happens, so that we are in this now this becomes our new universe. The probability that A happens is just it's the area of this region. Well, it's the proportion. You have to normalize it. So pretend that the area of this region is 1. So it's what proportion of this blue area is this red area. So that is precisely the probability of A intersect B, in other words, this area divided by the blue area. And here we have to assume that the probability of B is non-zero, otherwise we're dividing by 0, and this doesn't make sense. Okay, so maybe let's finish it by looking at an example up here. So suppose that B has already won the game. What is the probability that A has won the game? What we do is we just look at the blue circle, or the blue region, and we say what percentage of that is taken up by is also in. So this is the event that B wins, and what proportion of that area also corresponds to when A wins. Okay, so that's a good place to stop. Stay with us because in the next couple lectures we will do some more combinatorics, and we will look at permutations, combinations, and more complicated things such as multisets. Don't go away.